Volcanic winters. How dinosaurs rose to power after mass extinction. Imagine a world where the sun is hidden behind a veil of ash and gas, and the temperature drops so low that entire species are wiped out. This is exactly what happened 201 million years ago, at the end of the Triassic period, when a series of massive volcanic eruptions triggered a catastrophic chain of events that would change the course of life on Earth forever. Have you ever wondered what triggered the mass extinction that paved the way for the dinosaurs to dominate the Earth? It's a story that's been shrouded in mystery for centuries, but a new study has finally shed light on the dramatic events that unfolded at the end of the Triassic period. The Triassic period, a time of great upheaval about 201 million years ago, the Earth was a very different place. The continents were joined together in a supercontinent called Pangaea, and the climate was much warmer than it is today. But then, disaster struck. A series of enormous volcanic eruptions, known as the Central Atlantic Magmatic Province, CAMP, began to spew out vast amounts of ash and gas into the atmosphere. These eruptions were so powerful that they blocked out the sun, causing a rapid cooling of the planet. This phenomenon, known as a volcanic winter, would have a devastating impact on life on Earth. The Extinction Event. A turning point in history, the extinction event that occurred at the end of the Triassic period was one of the most significant in Earth's history. More than 70% of fossilized oysters and the mass extinction mystery. Ocean pH drop explained. Imagine uncovering a hidden clue locked away in ancient oyster fossils that reveals one of the Earth's deadliest environmental catastrophes. New groundbreaking research from the University of St. Andrews and the University of Birmingham has reconstructed for the first time ever how a dramatic ocean pH drop triggered a mass extinction event 201 million years ago. But here's where it gets controversial. This ocean acidification was caused by an enormous, rapid surge in atmospheric carbon dioxide, CO2, fundamentally reshaping marine life and ecosystems. Published in the prestigious journal Nature Communications, this study offers the first definitive evidence that ocean acidification, a decrease in the ocean's pH level, making waters more acidic, was a key driver behind extinction during the crucial Triassic-Jurassic boundary. Back then, the ocean was just beginning to see the rise of modern coral species alongside marine reptiles like plesiosaurs. Other ocean dwellers included ichthyosaurs, various fish species, and shell-bearing creatures such as ammonites and bivalves. One of the most striking impacts was the collapse of coral reefs, resulting in a reef gap that persisted for hundreds of thousands of years before coral ecosystems slowly re-emerged. While scientists had long suspected that acidification played a role in this extinction episode, they were taken aback by how sharply the ocean's pH plunged, the steepest drop ever recorded within the geological record. Researchers from St. Andrews, collaborating closely with their counterparts at Birmingham, meticulously analyzed fossilized oysters from this period to trace the ocean's chemical changes. These oysters act as natural archives, preserving signatures that unlock the history of ocean chemistry shifts and the devastating biodiversity losses that followed. The culprit behind this pH collapse was volcanic activity on a continental scale, linked to the initial breakup of the supercontinent Pangaea. This intense volcanic unrest released massive quantities of carbon, predominantly from solid Earth sources, which the team could chemically fingerprint with impressive precision. Interestingly, before this event, ocean pH hovered around 8.2, similar to today's average ocean acidity. However, the researchers determined there was a steep pH drop of at least 0.3, likely exceeding 0.4 units, equivalent to doubling atmospheric CO2 levels in a geologically brief window. For ocean species, it wasn't just the absolute pH figures that mattered. The rapidity and scale of this chemical shift proved catastrophic. Dr. James Ray, a reader at the School of Earth and Environmental Studies and co-author of the paper, emphasized the geological record vividly shows us that such massive releases of CO2 don't just alter the planet's environment. They acidify the oceans and precipitate mass extinction. This is a stark warning for us to act swiftly if we hope to avoid similar fates today. What makes this discovery particularly important is the clear connection it draws between fast carbon emissions, ocean acidification, severe disturbances to ecosystems, and large-scale extinctions. Notably, ocean acidification has now been implicated in 3 of the infamous Big Five mass extinction events in Earth's history, highlighting just how devastating this process can be. What's even more alarming is that the magnitude of the pH change seen 201 million years ago aligns closely with worst-case projections for our future oceans. That said, the speed of today's human-induced carbon emissions is far more rapid, potentially outpacing natural geological events and leaving less time for marine ecosystems to adapt. Adding perspective, Dr. Sarah Green, Associate Professor of Paleoclimates at the University of Birmingham and co-author, pointed out, this particular mass extinction unfolded over a longer time span compared to the lightning-fast pace of modern ocean acidification caused by human activity. Our findings should serve as a clear signal to ramp up efforts to cut greenhouse gas emissions, or else we risk pushing ocean chemistry to levels equal to or worse than those that wiped out massive portions of marine life in Earth's past. Does this ancient event suggest that the Earth's oceans have survived similar chemical upheavals before? Or are we facing something more unprecedented today? How should these insights shape our climate policies and ocean conservation strategies? We'd love to hear your thoughts. Do you think lessons from deep time can truly guide us in tackling modern environmental crises, or is current human impact something else entirely? Join the conversation and share your perspective below. Reference: Molly Trudgill et al., Pulses of Ocean Acidification at the Triassic-Jurassic Boundary. Nature Communications, 2025. DOI 10.1038/S 41467-025-61344-6. Ancient Apocalypse: How volcanic CO2 killed marine life 200 million years ago. Imagine waking up to a world where our oceans, teeming with life for millions of years, suddenly begin to collapse. This isn't science fiction. It's what happened around 201 million years ago, and scientists have just uncovered shocking new details behind this ancient ecological disaster. But here's where it gets controversial. The real culprit may sound eerily familiar to challenges we face today. A recently published study in Nature Communications has rocked the scientific community by revealing fresh evidence about the mass extinction that swept through marine life during the transition from the Triassic to Jurassic periods. Scholars from the University of St. Andrews and the University of Birmingham painstakingly traced this extinction to a dramatic surge in ocean acidification, driven directly by immense pulses of volcanic carbon dioxide, CO2, entering Earth's atmosphere. These findings not only illuminate the events of Earth's distant past, but also ring alarming bells for our planet's future. Using cutting-edge techniques like boron isotope analysis, a method akin to time traveling through chemistry, researchers scrutinized ancient oyster fossils. These fossils, which essentially serve as natural pH recorders, allowed scientists to reconstruct the ocean's acidity during this tumultuous era. The results? The ocean's pH plummeted at a rate never previously measured for this period, confirming just how rapidly and intensely conditions shifted. It's a discovery with massive implications. When the chemistry of our oceans changes too quickly, life struggles to keep up. And this is the part most people miss. The echoes of this ancient crisis are louder than ever in today's environmental discussions. The unsettling truth about volcanic CO2 and ocean life. Let's cut to the chase. Volcanic eruptions, especially those coinciding with Pangaea's slow breakup, propelled enormous volumes of CO2 into the atmosphere. Scientific estimates point to a drop in ocean pH by at least 0.3 units, and potentially even lower. If you're thinking, is that really so dramatic? Consider this. For marine organisms like corals, mollusks, and tiny plankton, all of which depend on stable calcium carbonate to build their shells and skeletons, even a small decrease in pH can prove absolutely catastrophic. shell formation becomes nearly impossible, threatening the entire foundation of oceanic food chains. Dr. James Ray, one of the study's lead authors, puts it bluntly. The geological record tells us that when there's a massive release of CO2, our planet faces transformational changes. Oceans become more acidic, and mass extinction soon follows. The major takeaway here is that quick surges in CO2 reshape our oceans in ways that threaten the very survival of marine ecosystems worldwide. Not everyone agrees on the degree to which volcanic activity alone bears the blame. Some suggest other factors may have played a role. What's your take? A race against time, then and now. What truly raises eyebrows and could spark fierce debate is how the speed of change in the past compares to what we're witnessing today. Dr. Sarah Green, a paleoclimate expert from the University of Birmingham, highlights a sobering reality. While the ancient extinction unfolded over thousands of years, current ocean acidification is progressing many times faster. And this time, humans are in the driver's seat. Combustion of fossil fuels, rampant deforestation, and other industrial activities are injecting CO2 into our atmosphere at unprecedented rates. Dr. Green explains, the Triassic-Jurassic mass extinction happened over millennia, but today's acidification is accelerating so rapidly, many marine species simply can't keep up. Want proof? After the ancient die-off, coral reefs vanished for hundreds of thousands of years, creating a painfully long reef gap in the fossil record. If emissions continue unchecked, we might not only repeat history, but experience an even faster, more devastating collapse of ocean life. Yet, there's debate. Could modern ecosystems, with their adaptive potential, bounce back more quickly? Or are we fundamentally underestimating the risks? Should governments be doing more? Or is adaptation the way forward? Chime in below with your perspective. Oyster fossils, unlocking secrets from ancient seas. The true genius of the study lies in the use of fossil oyster shells, nature's own environmental time capsules. By precisely measuring the boron isotope composition within these ancient shells, the scientists were able to reconstruct the exact acidity of the oceans during the extinction event. This method had never before been applied to the Triassic-Jurassic boundary, making the team's findings the most accurate yet. What did they uncover? The data revealed not just the extremity, but the lasting nature of the ocean's acidification. Marine ecosystems didn't bounce back overnight. Coral reefs, which today are vital for ocean biodiversity, disappeared from the fossil record for hundreds of thousands of years after the event. This shocking reef gap challenges the optimistic belief that oceans always recover quickly. In fact, the recovery was painfully slow, with permanent changes rippling through marine communities for eons. Here's the controversial bit. If our current emissions trajectory remains unaltered, today's marine life could be heading for a similarly grim fate. Should we be more alarmed, or are concerns exaggerated? What solutions seem most promising or realistic to you? Let's put it out to the community. Does this ancient warning change your perspective on how urgently we need to address climate change and protect ocean health? Where do you stand on the battle between technological adaptation and dramatic emissions cuts? Speak your mind in the comments. You might just change someone's mind or have yours challenged.